Okay, guys. So I think last class we did for C2V, and then I requested you to do the this for formaldehyde. I hope some of you have tried this, and we'll see if we have discussion time after this. We'll be able to discuss there, right? So let's start and go ahead what we have in the syllabus, and we'll plan accordingly. Okay. So this is actually I put the figure. This is actually ammonia molecule, and the ammonia I have specifically taken because you have C2V and you have C3V in the syllabus. So C2V, one of the example I have done for water. Now for C3V, ammonia is the simplest example. So I have taken ammonia, right? So, and strategy is exactly similar what we did for water molecule. Here also we'll take the two choices. One of the basis. One is Cartesian coordinate on each atom. Like here, this is the nitrogen. You have Z1, Y, X1, and Y1. Like this on each atom, this hydrogen, and this hydrogen, all of them are going to have the Cartesian coordinates, right? And now, of course, you have to realize that the way I have chosen the axis is Z is like going to the nitrogen and base triangle like this, middle of that, and it's basically perpendicular to the plane of the screen of the computer, right? And then X is along this, so that is X1 for nitrogen. That is because it is a non-planar molecule. Now Z is decided along C3, so XZ plane should contain maximum number of atoms. So in H, one of them if I take, so automatically this goes y-axis, and therefore so this one of the NH bond is on the XZ plane, right? So that is the choice of coordinate we are going to use. Now in the same fashion, we will have for hydrogen also Cartesian coordinates like X2, Y2, and Z2, like for second hydrogen, also similarly, and for the third hydrogen. These numbers 3 and 4 are indicating the number of atoms. Like N1, 1 stands for the nitrogen. This here it should be H2, and then H3 and H4. Okay, so now if we go to the next slide, you will realize the exactly in the same fashion what we did for water molecule, we are going to do it, right? So like in principle, you do it in the form of the matrices. Like we'll have 4 atoms, so 4 into 3, so 12 vectors. So it is going to be a 12-dimensional problem. So we'll have a matrix of 12 by 12, right? And then do sum the diagonal elements for each operation. You should get the character, but it's going to be getting complicated. So therefore, we will be using the number of unshifted atoms and then character corresponding to each operation for per unshifted atom, and then we multiply to get the total reducible representation what we get, right? So now if we look at for the identity operation for this ammonia molecule, so number of unshifted atoms is going to be of 4, right? That is going to be 4 because 1, 2, 3, 4, right? Now if I do C3, then it is C3 of course along Z, right? So now, and that is passing through the nitrogen, right? Now if I do C3, except nitrogen, all the 3 hydrogen atoms are going to be shifted location. So if I go clockwise, then this is going to come here, this is going to go there, and this is going to again go there, right? So therefore, number of unshifted atom is going to be only nitrogen, right? So that is 1, right? Okay, now sigma V, for the time being, I don't want to discuss much, but just assume that this is my sigma V, this one, right? So which goes along xz, right? So xz plane, if I take, then how many number of unshifted atoms is going to be there? Is all going to be only 2, right? So that is this nitrogen and this hydrogen, and these 2 are going to be shifting the position. So number of unshifted atoms are going to be 2 here. Okay. Now we look for the characters for each operation, right? Now for identity, of course, you know, this is going to, for Cartesian coordinates, 3 Cartesian coordinates, so it's going to be 3 because they do not change, right? Now for C3, what should be the character? Now you just simply recall that the character for rotational axis is going to be twice cos, then I'm going to have theta. Theta is the angle here, it is going to be 120 degree, right? And then plus 1, right? So that is for Cn, actual character for Cn. So n, depending on the n, I gave the theta value here. Now for here it is C3, so that is going to be 120. Now the value of 120 is going to be minus half. So this minus half, and this is 2, so that is going to be minus 1 plus 1, that is going to be 0, right? So the character for this is going to be 0, right? Now what about sigma V? Sigma V, of course, you know by now, its character is going to be 1, like, because if we take xz, both x and z remain unchanged, and y goes to minus y, so therefore it is going to be 1, right? So the character for each operations are going to be like this. So therefore the reducible representation of what we get, this number of unshifted atom multiplied to the character per unshifted atom. So if we multiply this, that is going to be 12, right? And then if you multiply this, that is going to be 0, and this is going to be 2, right? So it's a 12-dimensional problem. So identity, character under identity should be 12. I think that's what is compatible with that. Okay. Now coming back to the vector unshifted rule, I think we should be able to match these numbers. Let's try to do it. Okay. Vector unshifted rules, you already remember, it is on the screen itself, so you can see it. So now if I go for identity, I'm having 12 vectors, right? 3 on each atoms. So therefore, all of them remain unchanged. So therefore, I am going to get 12 character under identity. Now, if I go for C3 along Z, so this is the passing through the nitrogen, then vectors on all the hydrogen atoms, they're going to be changing the position. So each of them will contribute 0, right? So therefore, for the C3, only the Z, this Z1, rather you said, this remains unchanged. So therefore, this is going to contribute 1. Now, this and this, you have to think about, not unlike water molecule, they are having 120 degree. So this you have to think about in terms of the cos theta, right? So here we have to think about cos 120 for each of the vector. Right. So that is minus half. Right. So now Z1 is 1. Now when X1 rotates by 120, it comes somewhere here. So that is the contribution from this is going to be minus half. Again, Y1 is going to be somewhere here, right? So that is again going to be minus half. So that is minus half for this and this. So that is minus 1 and this one. So that is going to be 0. You might be wondering why we are not going to go for the negative. This is actually for, we discussed it is for the water molecule where angle was 180. So therefore cos 180 is minus 1, right? So in this case, exactly for other than 180, this minus 1 rule does not really hold. This should be actually the cos value. It should go like this, right? So this is what I wanted to discuss compared to your water molecule. So that's what I did it, right? So therefore this is going to be minus half. Y1 is going to be minus half, right? And then this is going to be 0 for nitrogen, and the rest of them are also automatically going to be 0 because they are all the vectors are going to be shifting, right? So therefore total is going to be 0, right? Now for sigma v, if I go along this, then what should be the value? Let's look at it. Sigma v xz, of course other angle automatically will come because they are in the same class, so therefore their character should be same. So let's go for only the xz, right? So this is your xz. Now if we do xz, what are the vectors? They remain in the same place, right? Now look at here. These are going to be changing, so their contribution is going to be 0 overall here. Now for these two, this nitrogen and hydrogen, like each of the Z1 and X1 is not, they are not changing. Z2 and X2, they are not changing because they are going to be on the XZ plane, right? So therefore their contribution is going to be 1 for each of them. So Z1 is 1, X1 is 1, Z2 is 1, X2 is 1. Now what about Y1? Y1 is going to go to minus Y1. So contribution for this is going to be minus 1, and Y2 also exactly same way, this is minus 1. So what is the total number then I get? So this is going to get cancelled. This is going to get cancelled, right? So then I'm going to have only 2, right? So therefore that's what you are going to get this number 2, right? So I think we are consistent with the vector unshifted rule, except that you have to remember here, I remind it again, this minus 1 does not hold anymore for Cn n greater than 2, right? So 2 is basically exactly reverse. That's what we use. So we have to, for Cn greater than n greater than 2, we have to like go for like this cos theta for contribution for each of them. Okay, so that's what it is. We are going to know it. Now, when we get this total reducible representation, now we are going to get reduce this in terms of all the irreducible representation of the point group of C3b, right? Let me clear this drawing, then Okay, so now I don't take all of them. I will take only A2, this number of A2, how it comes. So, and this is the character table. So we need to find out how many A1 or how many A2 or how many E they're coming under this total reducible representation based for Cartesian coordinates, right? Now then we will reduce the translations and rotation from this, that will come later on. But for the time being, I'm just picking up this one for particular reason because that will give you a little bit better idea, right? Okay. Now let's do it for A2. So this is Cartesian code, this is the reducible representation for total reducible representation. Now I want to find out how many A2 are going to be A2s are going to be appearing on this, right? Okay, so this is the reduction formula, what we know from the previous class. So if we want to go for this, let's do it, right? So I want to find out what is going to be number of A2 in this, right? So then how we do this? This is 1 by order of the group, that is going to be 6. Now for identity, this into this, for when the character is when the operation is identity, so R is identity, so I go for the character, so that is going to be 12, and then this is the character for the irreducible representation, A2 here, because I'm taking I is basically A2 here, right? So that is multiplied with 1, right? Then sum over R, so that the next R is going to be C3, so plus, right? So character is going to be 0 for the reducible representation multiplied with the character for the A2. Okay. Now, of course, you have to realize is that here I said that sum over should be all operations. Now here, don't get confused because I'm having two operations are here, C31 and C32. They belong to the same class. So that's why we are going for the 2 C3 and they're having the same character. So if I go for sum over R, I should have one more term like this, right? So one more term means instead of going for one more term, what I'll do, I'll multiply this with 2, right? So that is something like this. Right. Now, instead, what we can do like here, instead of summing over all the operations, what we will do is sum over the classes. So this is class 1, class 2, class 3, right? And when do the sum over classes, then we need to multiply the degeneracy of the class. Right? This one is here it is 2, here it is 3. So how this formula goes, now I'm replacing this R by RC. C stands for class, right? Then I need to multiply with the degeneracy of the class. So that is something like GC, degeneracy of the class. Now instead of operation R, I'm going to go for the sum over classes. So this operation, this is going to be now class operation under a single class. Again, this is for irreducible representation, that is also going to be under a single class, right? So in that case, if I'm going over class, I need to multiply the degeneracy of the class, right? So that's what is basically the number it comes from, right? It's 2. Now for identity, of course, I did not have problem, but this is going to be degeneracy is basically nothing but 1. So that is GC is going to be 1 for identity. So I really don't need to multiply. It remains unchanged, right? Now for C3, so this is 2. Now I hope this is a little bit clear. Now if I go for the sigma V, I'm doing over the class. So that is for the sigma V operation. Now GC, this the degeneracy is going to be 3 into character for the reducible character for the reducible representation, that is going to be 2, and then multiplied the character for the irreducible representation for which I am going to generate. So that is basically going to be -1. Right. So that is the number it should be there. Right. So what is this number? This number is going to be something like so this is 3 into 2 minus 6. This is 12, and this is 0. So I'm going to get 1 by 6 into 6, right? So that gives me 1, right? So that's what I have written here. If you look at here, this rows 1, right? Now exactly in the same fashion, if you do it for A1, you'll get this 3, and then if you are going for E, then you are going to go for 4. Like how it comes, you can very easily verify. So for identity, so for doubly degenerate representation, let's bring back the character table. Then you will be able to realize, like here the for doubly degenerate representation E, the character is going to be 2. So 2 into this 24, then this into 0, that is 0, this into this 0 into this, that is going to be 0. So it's basically 24 by 6, so that is going to be 4, right? Okay, I think that is clear by now. Otherwise we can discuss the if we get time, right? So clear the drawing, right? Now here is the numbers for the total reducible representation of what we get, that is 3A1 plus 1A2 plus 4E. Now I should be having total 12 numbers such that, because this is a 12-dimensional problem, that should be consistent. Like here it is 3 into 1 dimension, that is 3, 1 into 1 dimension, so total 4. Now this is 2 dimension, so 4 into 2, that is going to be 8, right? So that is 4 plus 8, that is going to be 12, right? So I think that is consistent. Now this includes all the motions, so that is translations, rotations, and vibrations, right? So from the character tables, we have to remove the translations and rotations. So then only we are going to get the vibration. This is pretty much clear what we did for the water molecule, and that's what we do this, right? Now for vibrations, like if we go for the total representation for XYZ minus translations and rotations, we should be able to get the total number, right? So let's bring back the character table, right? So character table, if we look at how the translations go, like this is Z Cartesian coordinates goes along A1, right? Then X and Y, they are doubly degenerate. Now within the parenthesis means they cannot transform independently, so they go simultaneously, right? So therefore this is E. So 2 is hiding here under E. So the A1 plus E, so that is basically the translation, right? Now for rotations, again you have to look at like this, RZ, right? That is E2, and then E, again Rx and Ry, right? So that is going to be something like this. So that is E. So that is going to be A2 plus E. Now if I subtract these translations and rotations from the total, so that is 12 over here, and we subtract 6 of them, so I should be getting total 6. So if you do it, it's pretty much clear that we'll get 2a1 plus 2e. Now here it is 2, right? So therefore it is 2 into 2, 4 plus 2, that is 6. So that is basically consistent with the 3n minus 6 we get. So 3n is going to be 12 minus 6, so total is going to be 6, right? Okay, so now like the way we have looked at the normal modes for the water molecule, here also we have to look at like this. So what we will now do is that to understand what are the contribution from the different bond angles and bond vector, right? So then only we will be able to figure out what is going to be the shape of the normal mode, right? So therefore I'm going to go for the bond coordinates now. Okay, so here you go, internal coordinates. Now here the way we define internal coordinates are like this. So this is R1, right? So this is R1, this is R2, this is another NH, this is R3, right? Now bond angles, of course, like this. So this angle is taken alpha 1, this is alpha 2, and this is alpha 3, right? So now that my number of variables are less, only 6, maybe I can think about going through the matrix representations, right? Also another reason is that, like if we look at this R1, R2, R3, and alpha 1, alpha 2, and alpha 3, so the bond vectors, they don't get interchange with the bond angles. So we can separate 3 bond vectors for 3-dimensional case, and 3 angles, alpha 1, alpha 2, alpha 3, again in a separate matrix, right? So that will simplify our life. So that's what actually I separated it. So we'll generate first this one, and then this one, and then we'll come back here, right? Okay, now if we look at this matrix, like I'm just going a little bit quicker because I hope you'll be able to pick it up. It's similar to your what we did for water molecule, right? So now we only concentrate now R1, R2, R3, because angles are not going to combine with this, right? So if I do identity, they remain unchanged, right? So therefore, it's going to be something like 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? So R1 prime is going to be R1, R2 prime is going to be R2, and R3 prime is going to be R3, right? So if the character under identity then is going to be sum of all these numbers, right? So that is going to be 1 plus 1 plus 1. So that is going to be 3 here, right? Okay. Now if we go for C3, again only one operation we need to do, because it's under the class we have the same character. So now the way this matrix is generated is like give the rotation anti-clockwise, right? So it was there, so I just picked it up. So anti-clockwise, if we give rotation, what it goes like this: R1 comes here in the position of R2, right? So that means new R1 prime should be written in terms of R2, right? So therefore, this is going to be 0, then 1, it is for R2, again 0, right? So that's why this row goes like that. Now for R2 anti-clockwise, it goes to R3, right? So therefore, this is R2 prime should be 0, 0, 1, right? Okay. Now for R3, exactly in the same fashion, we go for goes to R1. So therefore, this is going to be, this row is going to be 1. That means for R3 prime, it is going to be 1, 0, 0, right? So therefore, the character for this, you can get, this is going to be sum of the 0, 0, and 0. So character for this is going to be 0, right? Now, for sigma v xz, this is going to be again exactly in same way. Like if we do xz is along this, so that is going to be r1 remains unchanged. So that means it is going to be r1 prime should be r1, and rest of they are going to change. So change means it's r2 goes to r3, r3 comes to r2. So for r1 prime, it is going to be 1, 0, 0. Now for R2, it is going to be again, R2 goes to R3, so it's going to be 0, 0, 1. And R3 comes to R2, so this is going to be 0, 1, 0. So the character is going to be 1 plus 0 plus 0, so that is going to be 1. Yeah, I realize the time is coming up, so if it gets disconnected, we'll see. Right. Now, if we do it for the angles, bond angles alpha 1, alpha 2, and alpha 3, we should be having a matrix like this. Right, so it's exactly in the same way. If you can think for alpha 1, alpha 2, alpha 3 remains, they remain unchanged under identity. So that is going to be 3, right? So this is again going to be 3. Now if I do C3 along this z axis, so therefore it is going to be 0, because alpha changes, alpha 1 changes, alpha 2 also changes position, alpha 3 also changes the position either clockwise or anti-clockwise, it doesn't matter. So it's going to be 0. Now if I go for xz, right, then what you will realize is that alpha 1 and alpha 3, they are interchanging, right? That means alpha 1 will be written in terms of alpha 3, right? And alpha 3 will be written in terms of alpha 1, but this alpha 2 remains unchanged, right? So therefore, this is going to be alpha for alpha 2 is going to be, it remain unchanged. So this 0, 1, 0, but for alpha 1 is goes to 3, so that's why it is 0, 0, 1, and alpha 3 comes to alpha 1, so this is going to be 1, 0, 0. But again, the character is going to be 0 plus 1 plus 0, so that is going to be 1, right? So that is the reducible representations using the bond vectors only and bond angles only, because they don't interchange, right? So that is the reason we can do it. So then total it should be then the addition of these two, so that should be 6, right? And this is going to be 0, and this is going to be 2, right? So this is the internal coordinates. Now again, if you apply for the like kind of vector unshifted rule, we should be able to verify all these things. I think that we should be able to do it very quickly. If I go for this, like 6 of them, R1, R2, R3, alpha 1, alpha 2, alpha 3, all of them remain unchanged. So therefore, their character is going to be contribution for each of them 1. So that is going to be 6, right? Now, if I go for C3, right, so then all of them are going to be changing their position. So therefore, it is going to be 0. Now for sigma v xz, right, so 2 of them are not going to change, R1 and alpha 2. So therefore, it's going to be 2, right, like that. So this is going to give you the idea of what is going to be the reducible representation using the internal coordinates, right? So now let's reduce this. I'll do as long as it is allowing. So So let's reduce this in terms of irreducible representation. So I think we can do the reduction as we did for the last for Cartesian coordinates, or if you look at the character table, we should be able to look at just by inspection addition of these two, right? So now if I go for this, let's say 3 plus 3, 0, 1. Now how we can do this? Look at here. If I add A1 and E, right? So that is 1 plus 2, 3, right? So that's going to be 3. Then 1 minus 1, that is going to be 0, and then 1 plus 0, that is going to be 1, right? So therefore this can be written in terms of A1, right, plus E, right? Exactly a similar way we can get it for this one also, because the number are same. So we'll be getting A1 plus E, right? Now this definitely is going to be to sum of this, so that is going to be 2 A1 plus E, 2E, right? Right. So therefore this, look at here, it's exactly we got the same thing like what we got for Cartesian coordinates, 2A1 plus 2E, so total gives you 6. So 2 plus, here it is 2 into 2, total 6, right? So that's what we get it, right? Now here of course you can understand that they are going to be mixed up because both of them are A1 plus E, and this is alpha r vectors, and this is bond angle. So therefore we need to really watch what is going to be the normal modes, how they look like. Now here it's not would be that simple for the like a water molecule, because here is we have doubly degenerate representation. So you have to see which of the two modes are going to be doubly degenerate, right? So let's go slowly and look at it and see. Okay, here you go for the symmetric states. Now symmetric states, of course, you can realize is that is sorry, not this is symmetric state, this is symmetric bending. Sorry, just I correct myself. So this is symmetric bending. The way it is kind of umbrella motion, right? And in that case, the resultant vector goes like this. So it is basically along Z, right? And how do we get the representation of this, so that we can go for just looking at how it changes with the different operations, right? Now if we do identity, this remains unchanged, so that is 1. And if I do C3 along this axis, right, so bending of course it's remains unchanged. This is going to be 1. Again sigma v xz, so that is this plane if you are taking, because nh is going to be on this, so that is going to be 1, right? So therefore irreducible representation, it should be E1, right? Okay, then what about Raman and IR activity? Follow the same procedure what we did for water molecule. So I look at the character table. Now if you look at it, the character table, so to get the IR activity, what we have to go for the, it's any one of the Cartesian coordinates goes along A1, right? So answer is yes, because Z is transformed, Z is transforming as A1, so therefore it is going to be IR active, right? So that is IR, right? Now what about Raman? Raman, of course, like we have to go for this binary terms, right? So and again you can see that x square plus y square. Now here plus because it they transform simultaneously like this. So x square plus y square or z square, they both of them transform as like a1. So this is also going to be Raman active, right? Okay, so now we go for the symmetric stretch, right? So this is the symmetric stretch. You can think about all these vectors, how they are going to be connected. So that is like a resultant one is going to be, this one is going to be Q. So Q1 is going to be linear combination of R1, R2 and R3 like this, right? So therefore it goes along this, and it goes along similar to your what is like for the symmetric bending. So it is going to be something like this. So I really don't need to rewrite again, and of course it's going to be both IR and Raman active, right? Okay, now if we go for the next one, here you go, asymmetric stage modes which are degenerate, right? Now I should clear my drawing. Now in this case, look at here how this stretching, this is stretching, but this is in the different phase. So these two are in the same phase. This is in the different phase. So resultant is going to be along this. Now you can realize that this is going to be basically along minus x, because x is along this. One of the NH bond I have taken, so x is along this. So this is minus x, right? Now if we look at this one, right? In this case also you can look at here, this is almost remains unchanged. Now this is opposite phase, like if you remove this, is like similar to water molecule, what we go for asymmetric stage, and therefore this is basically kind of minus y, right? Now both of them are going to be behave in the same fashion, right? Now so asymmetric stage, what are going to be the character if you look at simultaneously? So it is going to be something like let's write this. So as both of them they transform like this, so I have to go simultaneously. So that is going to be something like 1 plus 1. So that is going to be 2, right? Now again when you do this rotation, you can see that the contribution from this is going to be when we go for C3, right? So this is going to be minus half, and this is going to be this is going to be minus half. So that that should be something like minus 1, right? And then when you go for sigma b xz, right? Both of them are going to change. Now how they are going to change now, this is going to be, if I go for xz, this is not going to change, so that is plus 1, and this is going to go to change, so that is minus 1. So this is going to be something like 0, right? So that means if we look at this, then character table, if we go for, then what do we get? This is nothing but your doubly degenerate representation, this, right? Now what about IR and Raman activity? That to do that, we should be able to get this character table, and we should be able to find out, yes, this is going to be IR active because X and Y goes along E, and also the quadratic terms, they go along E. So therefore it is going to be both IR and Raman active.